Okay, so in this segment we're going to cover strong inversion operation. So to start, we're going to establish a coordinate system. Okay, so if this is our MOSFET in cross section, and this is the source, the bulk, and the drain, and the gate above, we're going to call this direction the x direction, and this will be x equals 0, and this will be x equals L at the drain end of the channel. And we are going to recall from our discussion of the MOSFET operation in the last class we had on Friday before break, that in weak inversion the current flow is by diffusion, and in strong inversion the current flow switches over to being primarily by drift. And so the current by drift we can express as the mobile charge in the channel per unit length, which is going to be the width of the channel times the mobile charge density, Qm, which is the charge per unit area in the inversion layer. So this is the charge, mobile charge per unit length, times the mobility times the electric field in the x direction, and this will give us the drift velocity of the mobile carriers. And if you recall our basic electrostatic relationships, we can re-express the electric field parallel to the channel in the x direction as the negative gradient of the surface potential, d psi s dx. Okay, and so collecting this up, we can rewrite this as minus w mu qm d psi s dx. Now we're going to have to do something. Obviously we're not interested in expressing the current as a spatial derivative of position. We'd like just a current in terms of the terminal voltages. And there are two ways that people go at this point. Either they try to express Qm in terms of the potentials and integrate over potential, or they try to express the electric field in terms of the charge density and then integrate over charge density. We're actually going to take the second approach, and so we're going to need to find a way of expressing Qm, or rather d psi s dx, in terms of Qm. And so the rate of change between charge and potential is capacitance. And so if you think about our MOSFET here, we've got the source and we've got the drain, we've got some depletion region, and then there's some inversion layer right at the surface in the channel. From the standpoint of this inversion layer, we see basically two capacitances. We see Cox above us, and we see the depletion layer capacitance below us, C depletion. And so a little test charge, delta Qm, in the channel is going to be given by these capacitances in parallel, okay, because from the standpoint of this middle node here, we see these two in parallel. So we get Cox plus C depletion. If you recall, that's how capacitors combine in parallel, they add, times d psi s. And so we could call this effective channel capacitance, C equivalent. And so that basically tells us that we can express d psi s dx as 1 over C equivalent times dqm dx. And so therefore we can substitute that in and write I as equal to minus W mu over C equivalent times QM dQM dx. Okay? So now to get rid of this derivative with respect to x, what we're going to do is we're going to integrate both sides of this equation. Integral from 0 to L, from source to drain, of I dx on the left-hand side. And then on the right-hand side, we're going to have minus W times the integral from 0 to L of mu over C equivalent times QM dQM dx dx. That should be partial. So now we're going to move this outside of the integral and change variables on the right hand side, integrating over charge. The integral on the left hand side is simple enough. The I is constant as a function of position, and so that pops out of the integral, and we just get I times x evaluated from x equals 0 to x equals L. So the left hand side is just I times L, and the right hand side is going to be minus W times mu over C equivalent times the integral from Q at 0, QM at 0 to QM at L times QM dQM. Okay, so obviously we can divide the L, both sides by L, and find that the current I is equal to minus W over L times mu over C equivalent. Now this is an easy integral to do. It's just 1/2 of QM squared. Evaluated from QM at 0 to QM at L. So we can rewrite this as W over L times mu over C equivalent. Actually, we can put the 2 here, 2C equivalent, times QM evaluated at 0 squared minus QM evaluated at L squared. Now, this we're going to define as the strength ratio, S, and QM at 0, we typically call this Q source, which is the charge density at the source end of the channel, and we typically will call QM at L Q sub D. Notice here we took the minus sign from up here into the evaluation of this difference, and so we interchange the QM squared at L and the QM squared at 0 to account for that minus sign there. Okay, so this is the current as a function S mu over 2C equivalent of QS squared minus QD squared. So this gives us an expression for the current in terms of the charge densities, but what we would really like is an expression for the current as a function of the terminal voltages. So now we have to try to find a way of expressing those charge densities in terms of the terminal voltages. Okay. So if you recall, the approximation that we made when we were talking about the operation of the MOS capacitor was that up until we got to the threshold, every single charge we put on the gate went into creating the depletion region, sending away the holes, creating the depletion region, making that nice low energy spot right near the surface, the channel region for the electrons to flow in. And then once we got to threshold, there was low enough of an energy barrier that basically every additional gate charge we put on went into drawing another electron into the inversion layer from the source. And so basically QS is going to be equal to since it's the negative since it's negatively charged and it's the bottom plate of our parallel plate capacitor effectively, it's going to be minus Cox times the amount by which the gate voltage exceeds the threshold voltage, Vt. If Vg exceeds Vt, it's going to be 0 if Vg is less than Vt. And similarly, Qd will be the same. Qd will equal minus Cox times Vg minus Vt if Vg is greater than or equal to Vt, or 0 if Vg is less than Vt. We can rewrite this in terms of max, if you like. We could say that this is equal to the max. No, maybe I'll put a minus max of Cox times Vg minus Vt and 0. This is minus the max of Cox Vg minus Vt, comma 0, to basically account for these two different cases. Now, I want to think about what this threshold voltage is, right? So if you recall, we zoom in and just look at the source end of the channel. So you got this P minus substrate, and we got the gate sitting here. And maybe we'll draw the bulk here, bulk contact. We imagine, for the time being, that we have our source connected to ground and our gate connected to some potential. We'll call it the threshold voltage. Let's see. Vt. So this is a particular gate voltage that basically makes the depletion region under the channel the same thickness as the depletion region under the source region. And at that point we argued, since the depletion region width is monotonically related to the voltage drop, if you like, the potential difference across the depletion region. At this point, since the substrate is at the same potential, the potential at the surface is basically the same as the potential inside the N+ region, and so there shouldn't be any energy barrier for the electrons to get into the channel region. So I want to think about what happens if we were to raise the voltage on the source, right? So let's suppose we put some non-zero source voltage here. What would happen? Well, if we don't change this, what's going to happen? Well, the depletion region under the gate is going to stay the same, but the depletion region under the source is going to have to get a little bit wider, like so. And what that basically means is that we have increased the energy barrier between the source and the channel region, because now we aren't at this sort of equal thickness condition. And so in order to get back to the same position, which was just at threshold, we're going to need to increase the gate voltage. And we ideally need to increase the gate voltage by an amount that moves the surface by the same amount as we move the source. So we need delta psi s to be equal to delta Vs to get back to threshold. Now, if you recall, in order to move the surface, the only thing we can do is really move the gate, because the gate is not directly connected to the surface. And since some of the gate voltage increase will be dropped across the depletion region, and some of it will be dropped across the oxide, we have this capacitive voltage divider, right? So we get the oxide capacitance again, Cox, and the depletion layer capacitance, forming a capacitive voltage divider. And so delta psi s, we said on Friday, was equal to kappa times delta Vg. And so that means, if we set that equal to delta Vs, that the delta Vg that we need to put in to get back to threshold is going to be equal to delta Vs over kappa. So we have to move the gate by 1 over kappa times as much as we move the source to get back to the same. So if we add here Vs over kappa, we basically will increase this depletion region thickness under the gate to get back to the same place. And so the threshold voltage, Vt, at x equals 0, is going to have to be some nominal zero level, which we call Vt0. So this is the zero bias threshold voltage. And that's the value of the threshold voltage when Vs equals 0. That was the original threshold voltage. And there'll be a shift by the amount that the source voltage has been increased divided by kappa. So this is the threshold voltage at the source end of the channel. Because the drain has a different potential on it, the Vt at the drain, I should really put Vt of 0 here, and Vt of L here, and Vt of L here. Vt at x equals L is likewise going to be Vt0, the zero bias threshold voltage, plus whatever the potential is in the drain, divided by kappa. And so we can express Qs as minus the max of Cox times Vg minus Vt0 minus Vs over kappa and 0, and we can express Qd as minus the max of Cox times Vg minus Vt0 minus Vd over kappa and 0. Now, I'd like to do a little bit of work on these, and instead of rewriting both of these things over and over again, I'm just going to say focus on Qs. And what I'm going to do is I'm going to just factor out 1 over kappa from this term, and so we're going to have Cox over kappa times Vg minus Vt0 minus Vs and 0. And we can do the same thing for the drain, but this is really just to get a kappa times Vg in here and no kappa on the Vs, because that is more similar to our weak inversion model. And so running out of space here, so let's go back over here. And so we can express the current as W over L, which is the strength ratio, S, times mu over 2 C equivalent, times minus max of Cox over kappa times kappa Vg minus Vt0 minus Vs and 0 squared minus the max, actually minus max of Cox over kappa times kappa Vg minus Vt0 minus Vd and 0 squared. Okay, so obviously if we square this thing with a minus sign in it, the minus sign goes away, and since there's a 0 here, we can equally write that as Cox over kappa times 0, so we could actually take this Cox over kappa outside of the max without any difficulty. And so we can write this as S times mu over 2C equivalent times Cox over kappa times the max of kappa Vg minus Vt0 minus Vs and 0 squared, actually one more parenthesis, minus Cox over kappa times the max of kappa times Vg minus Vt0 minus Vd, comma 0 squared. Now we can take Cox squared over kappa squared outside and factor it out, and we get S times mu over 2C equivalent CEQ times Cox squared over kappa squared times max of kappa Vg minus Vt0 minus Vs 0 actually that parenthesis shouldn't be there and that parenthesis shouldn't be there and this parenthesis shouldn't be there and this parenthesis shouldn't be there. Okay. And maybe I'll call this max squared, like sine squared x max squared kappa Vg minus Vt0 minus Vs, rather Vd. Okay. Now, remember C equivalent was Cox plus C depletion. And kappa was equal to Cox over Cox plus C depletion. This is a capacitive divider ratio between the oxide and the depletion layer capacitance. And so this C equivalent here and one of these Cox's is actually equal to kappa. Okay? And so we can rewrite the current as the strength ratio times mu over 2 times one of the Cox's is left upstairs and one of the kappas is left downstairs times Cox over kappa times max squared of kappa Vg minus Vt0 minus Vs 0 minus max squared kappa Vg minus Vt0 minus Vd comma 0. Okay, and this is our complete strong inversion model. So we can get rid of this. So I'm going to flip over here to our slide deck that we were going through. And so here you can see this is not expressed in terms of the max. There's basically an if statement here that basically says that this is assuming that this quantity in parentheses here is greater than 0. So this is the expression for the current through an NMOS transistor. This is an expression for the current through a PMOS transistor with the gate source and drain voltages coming down from VDD. These would be negative numbers here. If the max term kicks in and this goes less than 0 for larger drain voltages, what happens is that this term goes away and we're left with the source term and the current saturates. For the PMOS, if we were instead to express the model in terms of gate, source, and drain voltages up from ground with some particular well voltage or bulk voltage, we'd have something that looks more like this, where every place up here in the NMOS expression we have a VG. We would put in the well voltage minus the gate voltage. Vs, we put in the well voltage minus the source voltage, and for Vd we put in the well voltage minus the drain voltage. Okay, so if we take this saturation case where we're at a large drain voltage and actually measure those characteristics, what we get is something like this. So this is exactly the same data as I showed you in the semi-log scale last time, only we're plotting now here on the vertical axis the square root of the current versus gate voltage, and you can see that we have this very nice straight line in the strong inversion region, and that indicates that we have a square law type relationship. So our model of that square relationship is pretty good. You can start to see up at this gate voltage of about 2.5 volts that the circles are a little bit lower than going, the centers of the circles are starting to get a little bit lower than this line, whereas down here they're going right through the centers of the lines, and that's due to a second order effect which is called mobility reduction. It turns out that as you get to higher and higher gate voltages, the vertical force, there's this increased electric field because of the larger gate voltage and hence more gate charge, which causes the electrons as they kind of go along the channel to basically get scattered up toward the oxide and bounce off the oxide, and that basically acts as kind of like a drag on the electrons, and they get a little bit less mobile than they are at lower gate voltages, and so this starts to bend over a little bit. But it's not a bad model. So if we look at drain characteristics, what we see is something qualitatively similar to what we saw in weak inversion, where we have at low drain to source voltages, we have this sort of Ohm's law-like characteristic where the current is increasing in proportion to the drain to source voltage. But then at high drain to source voltages, what happens is the current levels out. And so we call this region down here the ohmic region, as I mentioned before, where we have this Ohm's law-like, resistor-like behavior. And this region over here is called the saturation region because the current saturates. Mentioned in class that this is qualitatively similar to collector characteristics in the BJT, only in this unfortunate sort of coincidence of history, this region for the BJT is called the saturation region, which is exactly the opposite of what we call the saturation region in MOSFETs. So the saturation region in MOSFETs is the analog of the active region in BJTs, where we have this constant current source-like behavior. So unlike in weak inversion, where the saturation voltage, which is the boundary between the ohmic and saturation regions, is constant at about 0.1 volts, 4 or 5 thermal voltages, with strong inversion operation, we find that it takes more voltage across the transistor to saturate it the further up in strong inversion you go. And so instead of having a nice vertical line here as demarcating the boundary between the ohmic and the saturation region on this family of drain characteristics, we have this kind of parabola that opens up like so. And here the saturation voltage is basically kappa times Vg minus Vt0. This is actually Vd sat. Vds sat would be kappa Vg minus Vt0 minus Vs. Okay? So this upside down parabola is what the model predicts If you don't have that max in there in the model, what happens is that as you increase the drain voltage, this parabola that opens downward continues to go down, which is not what real transistors do. And so that's something you have to be very careful about. If you don't have the max in view, what happens is that you're blithely going to go forward with an equation that deviates from what the transistors actually do. So if you recall, that term comes from a charge density, and that charge density, when as you increase the drain voltage, gets smaller and smaller, and it doesn't go through zero. It basically goes into weak inversion, moderate inversion, then weak inversion, where the charge density asymptotically approaches zero, but it doesn't go through zero and change sign. So that's what's going on there. And let's see what our next slide is. Okay, this is a plot showing you what the surface energy looked like for an electron in the channel in weak inversion, where we had a constant surface potential, and we're going to think about what happens when we increase the gate voltage. So if we increase the gate voltage some, we push down the surface, and eventually we get to the point where we have a very, very low energy barrier here at the source, and we can't push down any further. And there's going to be a drop in potential as we go along the channel. But there's still a fairly large energy barrier here at the drain end of the channel. If we push down even more on it by increasing the gate voltage, we'll get to a point where there's practically no energy barrier at the drain end of the channel. And so what the device might look like in the ohmic region above threshold might be something like this. Okay? That's above threshold operation. In the next segment, we'll cover what we're going to do about moderate inversion.